Recording in progress.
So welcome to the master thesis defense of Lucas Trigal. I remind you, you have 30 minutes for your presentation, more or less. It can be a little bit more if needed, but not too much. And then there will be an undefined number of questions by the committee.
Okay.
So the floor is you.
So perfect. So good morning. So I'm going to present you my master thesis about information to energy conversion in autonomous thermal machines. And the theoretical background of this master thesis is the combination of these frameworks that have their roots in the beginning of the 19th century with the study of the thermal machines and the foundation of thermodynamics. Frameworks like the statistics of Boltzmann and the paradox of the Maxwell-Demon, the study of the quantum thermodynamics based on the ideas of open quantum system with the Lindblad equation, or the work in coherence of the coherence of Zurek, or in the 20th century, the study of the role of the information as a variable, as a thermodynamic variable with Landauer and Bennett, or the newest works in stochastic thermodynamics with the fluctuation theorems or the thermodynamics uncertainty relation. All these frameworks give us the tools to modelize these thermal machines or autonomous thermal machines. So the big reference that will be used in this master thesis are models that have been published the past years about this kind of autonomous thermal machines, or the role of the information as a resource for these machines. Okay, the structure of this master thesis will be, first I'm going to briefly discuss the theoretical framework, then the model, I will describe the model I have used, and then the results. First, the steady state fluxes with the first law and the second law, the thermodynamic regimes, and finally the fluctuations and probability distributions. So first, the Science-Hour system is an open system that interacts with an environment. We have modelized this interaction with the idea of collisional models. Okay, in the case of the microscopic model, we describe the environment as a group of different auxiliary units that interacts sequentially with the system. This is different to another approaches where the system is seen as a continuum and is all the time is interacting with the system. In this case, we are sequentially interacting with all the different parts of the environment. So the description of this interaction starts with the total Hamiltonian of the system and the environment, that is the Hamiltonian of the system, the Hamiltonian of the auxiliary units, and the interaction Hamiltonian. This Hamiltonian provides us the possibility of defining a unitary operation over the system. And we can compute for this time interval of interaction an analytic expression for this unitary operation that gives us the possibility of defining the state after the interaction for the compound state after the interaction of the system and the auxiliary units. That with this analytical expression we can derive the master equation for all the different parts of the system and auxiliary units. Okay. Another assumption that we made for the derivation of the dynamics is that the time interval between interactions follow a random distribution, in concrete a Poisson distribution. So based on this idea, we started with the state of the system after n collisions at a given time t. This expression is the integral over the time of three functions. One function gives us the idea of this waiting time distribution for a rate R of the Poisson distribution. Another term related with evolution of the system without the auxiliary unit, that is described with this Lindblad operator, that is the dissipation of in the case of the system without the auxiliary units, and then the state before the n collision. If we take the time derivative and sum over all the past n collisions, we obtain the master equation that is characterized by two contributions. One is the unitary contribution based on this trace over the Hamiltonian of interaction, and two terms related with the non-unitary evolution of the system. That is the dissipation, or in this case, is called a Lindblad operator, related with evolution of the system without the auxiliary unit, the dissipation process that have the system, and the dissipation based on the relation with the auxiliary unit. In this case, there are the operators of the system, and these are the operators of creation and destruction for the interaction with auxiliary units. For the case of the auxiliary units, we taking the partial trace over the Hilbert space of the system for the compound state. We have only the density matrix for the auxiliary units. We also have an expression for the state after the collision. Also have this unitary evolution and the term related with the dissipation or the non-unitary evolution of the system. So another framework that I have used in this master thesis is the inverse counting statistics. That is a part of the family of frameworks of the full counting statistics. The way you procedure in these cases is since in the previous framework we lost information about the interaction of the system with the environment, we introduce a more detailed analysis that give us more information about the probability distribution or the fluctuations of the system. So the way to proceed, we have an arbitrary system, and we have a detector for one transition. We have one state and the other state, and we have the transitions that go to 2 to 3 or 3 to 2. And we have a continuous monitoring detector that give us the information of the changes in these in these two states. So the idea is that we need to make a change in the previous master equation to encode the information in a counting field. And this idea is in the master equation or tilted master equation that we have here, these counting fields that encode information about this transition, maybe the 2 to 3 transition called a plus, and the opposite transition is the minus. And we have here this, we can with this master equation generate all the different cumulants of the distribution for these changes or stochastic changes. In this case, for the inverse counting statistic, is based on the idea of calculating the characteristic polynomial of the tilted master equation, and if we parameterize all the different terms with of this polynomial, we can calculate with them the cumulants of the distribution of these events. So with these ideas, we can have more information about this transition that happens between the state of the system. And finally, the last theoretical framework I have used is the quantum trajectories. In this case, we are looking for the case of continuous monitoring over the system, and we elaborate a modelization of the system that we compute the stochastic evolution of the system based on the ideas of that the change in the density state is based on measurement operators that changes the state of the system. In our case, we are only looking for two types of operator. There is no jump happen in the system, or a jump is detected in any channel. With these two measurements that we can be detected, we can compute an evolution or a stochastic evolution of changes or jump or no jump for give a long time. With this jump, with these jumps, we can calculate this kind of stochastic trajectories that at random times we have these jumps followed by no jumps, because the probability of having no jump is greater than the case of having a jump. So with this framework give us the possibility of compute the time evolution of the states given by the nonlinear stochastic Schrödinger equation. That gives the possibility of understand as jumps as random stochastic times, and we have this time evolution of the system for the operator of the changes in the channels. Okay. So now I'm going to present you the model used in this master thesis, that is the autonomous thermal machine. The autonomous thermal machines have two parts. One is the thermal machine and the other is the qubit states. The thermal machine is composed by two qubits, each of them coupled to a bath, a bosonic bath that with a temperature difference, with a coupling strength. And the dots has a gap of energy of EM. This thermal machine is also coupled with a strength G to a qubit tape. This qubit tape is energetically degenerated with the same energy of the gap. This will be the structure. If we look in detail this structure, we see that the thermal machine, based on these two qubits, have a Hilbert space of length 4. And the states where one qubit is in state 1 and the other in 0, or the other case, form a subspace of energetic, what is energetically degenerated. And this subspace is the two state that interacts with the states of the qubit state. So this subspace has an important role in all the future dynamics of the system, and also we can call it the virtual qubit of the system. That will have a virtual temperature that is the bias between the two reservoirs, and will be the main point of this interaction with the qubit that has the two states, the 0 and the 1. That are also energetically generated, and we can describe the density matrix, state density matrix of the system of the qubit state as, in the diagonal terms, the distribution population of the two states, 0 and 1, and if it has coherence, in the non-diagonal terms, the coherence of the system. So now the derivation of the dynamics, we start again, as I presented before, the compound state after interaction of the thermal machine and the qubit states that has this contribution of the interaction with the interaction terms and the Hamiltonian of the system and the qubit states. If we take the partial trace over the qubit's Hilbert space, we achieve the master equation for the thermal machine that has the term related with the unitary evolution with this function G, and the terms related with the non-unitary or the dissipators of the Lindblad operators. One is related with the evolution based on the head reservoirs, and is bosonic reservoirs. We have the rates based on this function typically for the bosonic reservoirs, and the other term related with the qubit states. In this case, we have here the transition related with the virtual qubit, and the rates are based on the distribution probability of the states 1 and 0. So the condition that will be satisfied in this for having this master equation are: first, we define magnitudes, this tau, the interaction interval, and the G, the coupling with the qubit tape, must be mass less than 1. That is, means that weak and fast collisions. Also, the relation time scale condition, the weak coupling, and finally, a relationship between the strength of the coupling with the high reservoirs and with the qubit state. So if we look for the case of the qubit state, we start again with a state of the interaction of the compound state, taking the trace, in this case over the thermal machine Hilbert space, we achieve an expression for the qubit states after the interaction. We have again the two terms of the two contributions to the states after the interaction. Also, this CTP map has a single fixed point that is related with the thermal Gibbs state of for the virtual temperature and the qubit state Hamiltonian. In this case, if we look where is this fixed point as a function of the population of the state 1 of the qubit states, we achieve this formula that will be used later for understand where is this fixed point in the representation of the results. Okay, if we now go to the results, we start with the steady state regime. For compute the distribution of probability of the steady state, we start with the condition of stationarity, and starting with this expression, and we elaborate to the dynamical matrix, we can compute this distribution and use it for the next calculus. If we look to the energy, we start with the idea of, since the interaction Hamiltonian preserve energy with the collisions, and also since the Cubic tape is energetically degenerated, there is no energy flux between the Cubic tapes and the Hamiltonian and the thermal machine. So since this change in energy is zero and the Hamiltonian interaction preserve energy, the fluxes between heat fluxes between the reservoirs must cancel out. So if we compute these heat fluxes for the case of stationarity and rewriting the terms based on the definition of the states or probability states of this distribution, we can obtain that in fact both magnitudes have the same expression but with a minus. So if we represent the result for a section of the Bloch sphere, in this case in the X level is the coherence and the Y level is the distribution probability of the state 1, we achieve that we have two possible regions. One where the heat flows from the hot reservoir to the cold reservoir, and another one where the heat goes from the cold reservoir to the hot reservoir. We have here, for the case without coherence, the classical case, we have here a point where both fluxes are equal to 0. This point is the equilibrium point that I mentioned before, and will be the main point for the case without coherence, because we have here that no fluxes will happen here, and maybe later other magnitudes also are 0 here. Another relevant thing that happen here is that for coherence, the amount of heat that goes from the hot reservoir to the cold reservoir increase. Coherence increase this amount of heat. Okay. Now, if we look to the entropy and entropy fluxes, we need to start by the total entropy production. In this case, the total entropy production is the sum of the entropy fluxes based on the reservoir and the entropy fluxes based on the changes in the tape. For the case of the reservoirs, is the typical expression of the heat fluxes product with the inverse of the temperature, but for the case of the Cubic tape, since it's energetically degenerated and there is no energy flux, we compute the change in the von Neumann entropy. This von Neumann entropy, since is the extension of the Shannon entropy to the quantum case, has a informational context interpretation. Is like the amount of the change of the information that we have since the distribution probability changes with the interaction. So the sign of this magnitude will be relevant to understand what is happening to the Cubic tapes or the information of this Cubic tape. If we rewrite this expression with the result that we have for the state after and before the interaction, we achieve this expression that have two contributions. One is classical contribution, that is this part, and a coherent contribution to the changes in the entropy of the system. If we represent this magnitude again for the section of the Bloch sphere, we find that we have two regions again. One where the entropy, a change of the von Neumann entropy is positive, and the other where the change is negative. Then, as we told before, since the von Neumann entropy has this informational interpretation, we can say that when the entropy, the change of the entropy is negative, we are losing information. We are erasing information. The thermal machine is erasing information to the Cubic tape in the Cubic tapes. And when the change is positive, we are writing. This idea comes from the the role of information, the Maxwell daemon, and the idea of as the Maxwell daemons knows more information about the system, or they are erasing information about the system. So for the case without coherence, we see that we have 3 regions. One is when in between 0 and 0.5, that we are writing information in the system, that the change by Newman entropy is positive, and another part which is negative, we are erasing, another part between the equilibrium point and 1 that is positive. The change of the shape of this region that is negative changes with the rate, the Poisson rate of the system. As the rate increases, the shape increase and take a form of a raindrop as the rates increase with the rate increase. Okay, so the total entropy production in this case represented for the case without coherence and for the section of the Bloch sphere, we see that in the case without coherence, we have the minimum entropy production having equal 0 at the equilibrium point, since all the different magnitudes are equal 0. As the coherent increase, we see that production of entropy also increases. If we now look to the thermodynamic regime based on the idea of, okay, we have the head fluxes and the entropy fluxes, we can define 3 regions. Refrigerator, eraser, and dissipator. When the heat goes from the cold reservoir to the hot reservoir and the change in the von Neumann entropy is positive, we call it that is refrigerator, related with the idea of the daemon is knowing more information or is taking information about the system, so we can have this flow from the cold reservoir to the hot reservoir. Another section called eraser, that is related with head flux from the hot reservoir to the cold reservoir, and we are a negative change in the von Neumann entropy. And the last region, the dissipator, that is a head flows from the hot reservoir to the cold reservoir, and we are increasing the amount of information in the qubit states. We see the bigger region is the dissipator, and in the case without coherence, the changes of the different regimes are related with the entropies that we defined before of the qubit states and the virtual qubit temperature. When the virtual qubit is less or is greater the virtual temperature than the qubit temperature, we have in the refrigerator regime. When the qubit temperature is inside 0 and is greater than the virtual, we have eraser, and the other case we have that is the dissipator regime for the case without coherence. If we now look to the case of the efficiency, and we compute the COP, the efficiency, the refrigerator efficiency, we see that the maximum of the efficiency is near to the equilibrium point. If we increase the population of the qubit state 1, we decrease the efficiency going to 0. And for a given population, and we increase the coherence, we'll also lose efficiency for the refrigerator regime. This gives the possibility of optimization the performance of the refrigerator, gives us the necessity of thinking about which efficiency we want for the maximum heat that goes from the cold reservoir to the hot reservoir. And as we see, as we change the parameter and we change the shape of the area of the region of refrigerator, since always the maximum efficiency is near to the equilibrium point, that is changing and going up to a biggest population of the state 1, we see that if we want a greater efficiency, we have a less amount of flow of heat. If we increase the heat that we want to go from the cold reservoir to the hot reservoir, we have less efficiency. If we now look to the case of the eraser, we see again that the maximum efficiency for the eraser is near to the equilibrium point, decreasing as we go to a less population of the state 1, and again with the coherent we lost efficiency. In this case, we see that going to 0.5 from the equilibrium point to 0.5, we decrease the efficiency of the system. So maybe here the optimization of the performance of the eraser will be related with the maximum amount of information that we can erase for the for the system. So if we change the variables of the parameters of the system, like the energy gap or the difference of temperature between the reservoirs of the thermal machine, we achieve that for a given configuration of the energy, we have a minimum amount of information that we can erase, that we can also change or increase this minima, changing the parameter. And we can achieve that as the temperature of the cold reservoir goes to 0, we have a biggest amount of information that can be erased, and we have a optimal configuration that is for this energy near and a difference between the temperature of the system. Okay, now if we look to the fluctuations, we start with the again with the ideas of the I told before of the inverse continuous statistics, and we need to make a change since we are dealing with this transition between the qubit state and with the head reservoirs, and since we don't want to lose this coherence, we need to make a change in the Lindbladian expression that I present in the previous section. In this case, we make a change, eliminate the unitary evolution with this property that the Lindblad form has for changing the form. In this case, we have used this expression, and we achieve this master equation having only the Lindblad operator with the counting fields for the cold reservoir, the whole reservoir, and related with the qubit states. With this master equation, we compute the characteristic polynomials, and this parameterization of the polynomial characteristic polynomial, we can describe the analytical expressions for the mean current and the variance of the currents with these parameters of the polynomial characteristic. Okay, for example, we can compute the variance for the heat flux of the cold one, and we see that the minimum variance of the head fluxes is in the classical case, and as the coherence increase, we see that the variance also increase. So it's related with the increased amount of fluctuation that we have to the system. Related with the study of the fluctuation, we can compute the TUR, the thermodynamic uncertainty relation, that gives us which is the best configuration of the optimal state of the system to have a detection, or where is the fluxes, the head fluxes, and the fluctuation give us the better better action or better chemical regime. Equal or greater than 2, being the equal to 2, this optimal configuration for detection. And in this case, as the coherence increase, we see that we are going up to 2, a greater result. That is, in this case, related with this the idea that we have more fluctuation and we don't have a perfect detection. And the minima is for the case without coherence being equal to at the fixed point. The equilibrium point, in this case, give us the better detection of the head fluxes and the variation. Okay, so finally going to the cases of the efficiency fluctuation, we have used a framework given by the large deviations. In this case, we have the expression of the probability distribution of the head and entropy distribution of probability, and one for the efficiency distribution. In this case, we use this expression that called large deviation that are related with long trajectories. We can compute these functions for this long-term limit. In this case, we have a relationship between these two magnitudes, and we have an analytical expression. We can compute the expression in the limit that is close to the equilibrium, that are we can approximate this distribution as Gaussians. Demonstrate that our variables are close to the equilibrium, we can approximate it as Gaussians. We can compute this large deviation function for the case of the heat and the entropy. We have the marginal distribution, and we can see that is near to the result based on the idea of the are Gaussians or are close to equilibrium. So if we now compute the expression for the probability distribution of the efficiency, we achieve these results that are the efficiency fluctuations for the efficiency fluctuation. Okay, these functions have relevant points. These are related with the probability of achieving this efficiency for the different trajectories that we have simulated, stochastic trajectories. When this function is has a minima, is the most probable efficiency we can achieve. In this case, is the this is the average over the trajectories. This is the efficiency that we achieve in the case of the previous section. This is the mean efficiency, and we achieve the maximum for the Carnot efficiency that is related with the minimum probability. Is the less probable efficiency we achieve for these trajectories or stochastic trajectories. And we also have an expression for the tails of this function. So now if we look to the probability distributions, we see that for the head and from the hot heat and from the cold reservoir, we see that, okay, our results give us in the mean a similar expression to the analytical results, but also we need to say that in this case the distribution is similar to a Gaussian, but it's a discrete distribution. We only have possible values for the distribution for a given point that is related with the energy gap of the system, and we have this discrete distribution for the heat. For the case of the entropy, we have again that there is a negative change for this configuration of the von Neumann entropy, and we have also the tails that are asymmetrically with the changes in the more negative trajectories, with a more negative change in the information and the positive changes. And then finally, the entropy production distribution. In this case, for the case of the quantum trajectories, we have another definition of this entropy production, that is related with the head fluxes, with the change in the tape, and also since we are dealing with a scheme that is with a measurement in the beginning and the end of the trajectories, we have that entropy production along the trajectory. These changes are, so in this case, have this form that is related to the probability of the initial state and the probability of the final state. If we compute also this entropy production, must satisfy that the fluctuation theorem must be equal 1. And in this case, we achieve also that is near to 1. So also another thing that's relevant is that the form of this distribution. And we have these peaks that are related with the idea of science, the entropy, the head, the distribution probabilities are discrete. These peaks are related with these peaks of the distribution. And as we see, the mean is positive, but we have the possibility of having trajectories where the entropy production can be negative. So finally, we have described a system that works with the possibility for conversion of information to thermodynamic tasks, to the different efficiency and where is the maximum efficiency of the system for the near to equilibrium point, the role of the coherence with this decrease of the efficiency, and also we have computed the fluctuation of the system with the Tour. The Tour is always greater or equal than 2. And we have studied the different fluctuation of efficiency and the probability distribution. Also, other results that I don't present here are the relationship with other types of microscopical models, like the weakly coherent collisional models, or the study between the more detailed study of the optimization. But for this time, I can do it all these results. So thank you for attention, and that's all.
Thank you, Lucas. So we'll start with the questions. So Rosa, do you want to go first?
Okay. Yes. Yes. No. Because I have to say that